Mr. B. Dhanasegar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science, and here we are having the subject compiler design. So, in the previous episode we have seen that is bootstrapping of compiler and also the compiler construction tools. The compiler construction tools make the compiler design much easier because we will try to build up the compiler from various tools which are already existing by specifying the languages, syntactic and lexical constructs. So, the token structures and the statement structures, if you provide for the compiler construction tools, they will be able to build up the various components of the compiler, and by integrating them we will be having the compiler of our requirement. And the bootstrapping of compiler answered the way in which the first compiler was generated, because the program which is a compiler is also written in a programming language which is supposed to translate a programming language. So, who has translated the program in which the compiler has been written? So, the question was answered by the bootstrapping of compilers. Now, we have the lexical analyzer, that is the design of lexical analyzer and the implementation of lexical analyzer for any token specification. So, the first one is going to be what is going to be the role of the lexical analyzer. So, what it is doing. So, it reads the source program because it is the only phase which operates character by character from the source program. So, this will be a time consuming phase also, which reads the source program and group them into logically cohesive elements called that is lexemes. So, for example, if I am having a statement like that is if, or I can take for example an assignment statement A is equal to B plus C. So, first it will read A, which cannot be combined with equal. So, A will be one cohesive element which is called the lexeme, and the corresponding token will be ID followed by the pointer to the symbol table where this identifier will be installed, and followed by another token will be returned as it is equal which is the lexeme also, and next we will be having B, which is the lexeme whose corresponding token is going to be ID followed by 2, and once again a plus is returned which is the lexeme as well as the token, and finally it is going to be C, which is the lexeme whose corresponding token is ID followed by 3. So, this specific string of tokens will be returned as a pair of that is information, so that the parser can read and interpret them in the proper way. So, that is being the that is the role of your lexical analyzer. So, it produces sequence of tokens from that is each lexeme in the source program as output, and another important thing which is being done by your lexical analyzer is that is every token it finds, that is especially the class of string type that is tokens, they all will be installed into the symbol table. So, we will be having a symbol table which records every identifier, that is those identifiers will be installed into the symbol table during the declaration itself. So, once you find a declaration, we can find out what is going to be the type of the identifier and what is going to be the size of the identifier. Sometimes if the declaration comes with some initial value for the variable, you can even define the variables in the initial stage itself. So, certain attributes of your there is identifier can be collected during the first phase of your compilation, and certain attributes can be collected during the syntax analyzer. So, everything will be installed into the symbol table, so that further phases can read and interpret the values from the symbol table. So, it does two things. One is the that is formation of tokens which will be returned in terms of stream of tokens into the symbol or syntax analyzer, and the second one is it is installing the identifiers into the symbol table. And another job is also being done by your lexical analyzer, That is, whenever it finds that a stream of characters which could not be converted into a proper valid token as per the specification of the token structures given in the form of regular expressions, then it will report an error. So, whenever a valid token cannot be identified or obtained from the remaining input which is yet to be scanned, then your lexical analyzer will give you error message. So, now you can describe the entire process in a diagrammatic manner. You have the source program here, and which is given as input for your lexical analyzer, and you find that there is a parser also involved here. Parser is, I mean, the syntax analyzer, whose output will be given to the semantic analyzer, which is the next phase which follows the parser. And you can say a bypass direction here. One is what is going to be the token, and another one a request from the parser, which is get next token, which is given as input for your lexical analyzer, and these two are that is interacting with the symbol table. So, we must understand that the parser is using the lexical analyzer not as a separate phase, but as a coroutine, so that any requirement for a token by the parser will be immediately sent as a request to the lexical analyzer to find out the token from the next input. So, for example, if you are the parser is verifying an expression. So, if for example, it is going to be a binary expression with an identifier plus another identifier. So, the first ID has been obtained and plus has been obtained, and if it is going to be the another identifier to be obtained by the parser makes a request for the lexical analyzer or the scanner to send the next token, and it will find out whether the next token is an identifier or not. So, if the next token is an identifier, then it will go ahead with the remaining processes like constructing the parse tree. If the next token is not an identifier, rather if it is going to be an operator, immediately your parser will report an error message. So, instead of finding all tokens together and flushing them everything into the syntax analyzer as a whole, the syntax analyzer initiates the job. That is, whenever it finds a token, it needs a token for the construction of the parse tree, it will make a request for the lexical analyzer or the scanner as get next token, and it reads and processes the token. So, that is what the diagram says. And the need for the lexical analyzer is also a very important thing, because we say that the syntax analyzer uses the lexical analyzer as a coroutine. So, coroutine means why can't the syntax analyzer can do the same job which is being done as a lexical analyzer instead of going for a separate phase. The first point is, so these two are recognized by using two different kinds of recognizers. One is by the regular expressions, which is whose implementation is available in the form of finite automata, and the another one is called the context free grammar, whose implementation is available in the form of push down automata. So, constructing grammar or constructing push down automata or the recognition of strings with the help of push down automata is little difficult when you are comparing with constructing a finite automata or recognition of string with the help of finite automata kind of things. So, if you are that is having a separate phase for lexical analyzer, then the construction of the lexical analyzer will be easier, because it is going to have the complexity as the complexity of your finite automata construction. But in the case of that is, if you combine the lexical analyzer along with the syntax analyzer, so we need to write for every write grammar for every syntactic, sorry, every lexical structure, that is, so that even for a very small lexical structure, maybe for the identifier recognition or for recognizing an operator, we must come up with the grammar, and then the grammar will be converted into a parser or the push down automata, so that the process will be accomplished. So, having provision for constructing a finite automata, if you go for a push down automata, it is unwantedly complicating the process. So, that is the reason why. So, we start with a lexical analyzer whose recognition tool is going to be finite automata, and which in turn will give you that is a scanner as an outcome, and which will be used by your parser. Another point that we have to remember here is during the that is the reason for the split is, so if we keep them as two different phases, then the design of lexical analyzer and the design of the syntax analyzer are much easier than constructing them together as a single phase. These are the reasons why we are going for lexical analyzer as a separate phase. So, this is what the explanation. It is simplifying the overall design of the compiler when you go for a lexical analyzer phase. And very important thing is the structure of the lexical constructs like the keywords, the operators, the constants, identifiers. So, they all can be very easily represented by using regular expressions, and the overall there is overhead in the design of the parser can also be reduced. That is, if you are combining the role of your lexical analyzer along with the role of the parser, the overall design complexity in your parser will be high. So, which is going to be eliminated by separating the lexical analyzer as a separate phase. So, now the lexical analyzer actually it is keeping track of line numbers, whereas it strips the white space such as redundant blanks and tabs, and it deletes even comments. So, that is what normally being done by our lexical analyzer, because they are not part of any valid or useful tokens. So, we will do that elimination of and all. So, there is another concept called that is input buffering, which is needed for when we are going for recognizing the tokens. It is because of it is like we read source program from the file, and it is the characters will be read one by one. So, we cannot load the entire source program directly onto our random access memory. So, we will load it by parts, some portion of your text and then another few lines and another few lines, like that only. We will load and then it is translated into stream of tokens. So, during the loading process we may find that there will be two number of pointers. One is called the beginning, token beginning, and another one is called the look ahead pointer. The token beginning pointer will be pointing to the starting place of your token, and the token look ahead pointer will be pointing what is the most recently processed character. So, now if you are having these two things, but if you are not able to have the token beginning and the token end in the buffer, then it will be very difficult to find out the extract token after reaching the token. So, that is what we divide the buffer space into two walls, so that whenever we find your first half has been emptied or it has been completely processed, then we will load this second remaining amount of text or the source program into the first half, and we will continue with the remaining half. So, that we will be always able to ensure that the token beginning and look ahead pointers will be under our control. By separating or by extracting the text in between the token beginning and look ahead pointer, we will be able to find out what is the exact token to be processed. So, it is because of the tokens, as long as the tokens are going to be very smaller in length, there is no issue with it. But the tokens, if they are very long in nature, that is, while scanning for tokens, many characters beyond the next token may have to be that is examined some cases, because we do not know whether we have reached the right end of the token or not. By exactly reaching the right end, sometimes we need to read more number of characters, and after that, after finding the token, that is your next symbol, we will find that we have to skip few more symbols, so that we will be able to find out a valid token. So, it is actually we are making the lexical analyzer to read from its input buffer, and one of its implementation is we go for buffering the that is scheme, where we will be having a buffer of size 200 characters divided into two equal halves, where two number of pointers are implemented. One is the token beginning, and another one is called the token that is last, or we will be saying that it is a look ahead pointer. And one pointer, it is marks the beginning of the token being discovered, and the look ahead pointer scans ahead of the beginning pointer until there is the token has been discovered. So, that is what the job being done by your that is your input buffering, so that we will be able to extract the token in an efficient manner. The next is the design of your lexical analyzer. So, given a specification, that is, we shall construct the lexical analyzer from the that is token specification. So, we shall go for a short break. After that, we will continue the design of lexical analyzer. Welcome back. So, we have seen the that is your input buffering concept. So, now we shall see how we are designing a lexical analyzer. So, first of all, you should know that is what is needed for the design of a lexical analyzer. So, the requirement is what is going to be the token structure for your the tokens. So, once you know the token structure, we can very easily come up with the regular expression for that. and the regular expression can be transformed into finite automata, and the finite automata can be transformed into a C program or C++ program, which can be compiled to produce a valid scanner. So, we should know what is a regular expression, and we should know that is what is a finite automata, and then we can find out the methodologies being followed for translating the regular expressions into its equivalent finite automata, and the finite automata can be translated into the programs by using the tool called Flex kind of things, which is there in the Linux operating system. So, here we have the transition diagrams, so which are going for the representation of your lexical analyzer. So, transition diagrams are the specialized kind of tools used for the design of lexical analyzers, and so they have very limited power in terms of the remembering. So, it can remember only the previous character, but not too much of history can be remembered by your transition diagram. So, it is going to be a transition diagram means we will be having some notations like small circles, they are denoting the states of the transition diagram, and then we are having small arrows which will be called as the edges, which are connecting the various states available in the transition diagrams, and all these edges are labeled with one or more number of symbols from the alphabet of the language. So, for example, if you are talking about the operators of your C programming language, so the labels available in the various edges are the operators of the C language programs, and so actually those characters which are appearing on the edges are the labels as edges as labels are the characters which we are supposed to recognize. So, if it is a plus, then we may say that plus is the symbol which we are supposed to recognize as part of your recognition process. So, now we shall see that is how we are having a transition diagram for an example, like we are having a transition diagram for an identifier. You see that the start state is 0, which is a small circle with some identifier which is telling you what is going to be the state of this transition diagram, and then we are having the state number 1, then we are having state number 2, we have 3 number of edges, one is from 0 to 1 and another one from 1 to 1, and the third one is from 1 to 2. So, 0 to 1 is labeled as letter, which means that it is possible to move from the state number 0 to state number 1 only if a letter is going to be the first symbol of the identifier, which is like from the remaining input, that is which is yet to be parsed, yet to be scanned or yet to be tokenized. You read the first symbol, if it is a letter you are going to the state number 1, and from that onwards we just recall the rule for an identifier. The rule for an identifier is a letter followed by letter or a digit any number of times. So, here we are having a letter or digit, for that we have a valid move from 1 to 1 back itself. So, next is that is whenever you find a delimiter, for example, if it is going to be a plus followed by the identifier or a semicolon followed by an identifier, or there is a closing bracket followed by an identifier, then they all will be considered as the delimiters for that context. So, now on seeing the delimiter we are in state number 2, but actually the delimiter is not part of the token. So, the token part is starting from 0, that is a place where your beginning point is there, that is token starting pointer is there, and it is only up to the state number 1 we need to backtrack, that is we are backtracking from state number 2 to state number 1 to reach the actual end of your that is your token. So, that is nothing but 1. So, whose label is going to be letter followed by digit. So, after backtracking from 2 to 1 we will be in the rightmost end of the token. So, extract the token which is covered in between 0 and state number 1. So, delimiter will be completely that is truncated. So, that is what the explanation here, that is the starting state is 0 and an edge from 0 indicates that the first input character must be a letter, because there is exactly only one transition available, and then we are entering into the state called 1. So, which is looking for the next input character. So, the next input character is a letter or a digit, and then we enter into state number 1. So, this process is repeated until the next character is going to be a delimiter. Once you find a delimiter, then immediately we can there is backtrack to the previous position to find out the exact token being recognized. So, after entering the state 2, so which is an accepting state, so what do we do there is we will go for installing the token into the symbol table. So, that is a very important one. So, we entered into the state number 2, then there will be a corresponding, that is install routine being called by your scanner, which stores the symbol into the symbol table or the identifier into the symbol table. So, the equivalent procedure version of your that is your transition diagram is given here. So, what are the things happening in state number 0? It is you are going for a get character. So, if it is a letter, then go to the state number 1. If it is not a letter, then you can immediately say that we failed to recognize an identifier, then quit out of this recognition process. But that may be a valid token which is a different one, maybe a constant. Suppose if the that is letter is going to be a digit, there is a character whatever we have read as a digit. So, it may be for a constant, but not part of an identifier. So, in that case the token recognition must start with a different state, but if it is starting with state number 0, then we can have a valid move only for the letter as per this design is concerned. So, which will be a progress for identification of the identifier, but not a constant. So, now we are in state number 1. So, where what do we have is there is a character, once again we read it, you find whether it is a letter or a digit. So, if it is letter or a digit, then I can go to the state 1, and if it is a delimiter, then we are going to the state number 2. So, otherwise we will fail to recognize an identifier, that is either it must be a letter or it must be a digit, and if it is going to be a delimiter, then we will go for S2. So, when what will be happening in the delimiter state, that is delimiter state means the state number 2. When you are in state number 2, we go for retract operation. So, the retract operation is needed for just truncating the delimiter which has been already recognized. So, once you truncated the delimiter, then what will happen is we are in the rightmost end of the token. So, we know what is the beginning of the token and what is the end of the token. So, in between them we have some number of sequence of symbols, and that will be forming your identifier, which in turn is supposed to be installed into the symbol table. So, the state number 2, what it does is it says or it flags that a valid identifier has been recognized, return that identifier and install it into the symbol table. So, that is what the job being done by your finite automata, the finite automata, or you can even say that the transition diagram. So, now if you are given the regular expression, so here the regular expression is L followed by L or D any number of times. So, there is a letter followed by letter or digit any number of times is the regular expression for this pattern. So, the next topic is actually how we are recognizing the that is how do you write the regular expressions. So, they are simple expressions, but their intention is to construct that is valid regular expressions or valid lexical analyzers. So, how we are writing regular expressions from the overall language specification or the token specification. So, the simplest definition is we have certain notations, one is called the epsilon notation. So, we have here so the epsilon is a regular expression which is denoting the epsilon. So, for example, if you are interested in defining an empty string, so which does not have even a single position for storing a symbol, then now the question is how will you describe that. So, we cannot have a blank there. So, we must have some notation which will be describing the empty string. So, what is the notation is going to be epsilon. So, epsilon is a notation which describes the empty string, and then suppose if you want to have some regular expression, that is A. So, A is regular expression. So, then in that case what is going to be the language. So, A is any symbol, it can be A or it can be plus or it can be minus or it can be opening bracket, can be dot, anything. So, if you are having that symbol alone as a regular expression, then what should be done is you just that is return the languages the set containing only that symbol. So, that is going to be a dot or a semicolon or a opening bracket. And suppose if you are having there is very long there is regular expression, sorry, very long token, a lengthier token or a complex token, then those tokens are identified by making use of certain operations. One is called the that is union operation, another one is called the concatenation operation, another one is called the closure operation. So, if R and S are two different regular expressions denoting the language called the LFR and LFS respectively, then so what do we have here? So, we have three different languages being generated there. So, one is called that is either LFR or LFS. So, the regular expression which is denoting the language called LFR that is union LFS, that is a string either from R or a string from S, but not from both R and S. So, that is the meaning of the intersection operation. So, for example, if it is going to be plus or minus, then that is going to be a new regular expression with the language containing plus comma minus, but either you can recognize a plus or you can recognize a minus, but you can't recognize plus minus or plus plus or minus minus. So, that is about your union operation. And the second one is the concatenation operation. So, we have once again two regular expressions, one is R and another one is going to be that is S. So, now the concatenation is supposed to be a part of a string is formed by taking a string from R and another string from S, and we will write the strings in that order, that is R followed by S. So, and the regular expression is denoted by that is L of R dot L of S. So, it can be something like if you want to form a compound operator like that is your plus plus, there is unary operator plus plus or a compound operator plus equal, then your R is going to be first plus and S is going to be the second plus. You just combine them, R dot S, you will be having plus plus as an increment operator. Or suppose if you are interested in forming the keyword IF. So, I is from regular expression R and F from regular expression S, and now we can combine I and F to get a new regular expression called IF. So, that is about your the concatenation operation. And finally, we are having another one regular expression which is called the closure. See, for example, if you want to repeat certain things for more number of times, as we have already seen that the identifier syntax is going to be, or the lexical structure of the identifier is a letter followed by a letter or digit any number of times. So, the closure operation is a very important operation as far as any that is language construction is concerned, because most of the time the languages are going to be infinite. A concatenation will not give you an infinite language, or that is union operation will not give you an infinite language. But if you are concerned about languages which are having infinite number of strings, and they are as a result of the that is your closure operation only. So, which is having a regular expression, that is an unary operation, that is your closure is an unary operation, union and concatenation are binary operations. So, having a unary operation, that is a regular expression, how many times we repeat it. So, in the that is identifier case, suppose if you are interested in having L or D for any number of times, then put a star on the as the operator, which is a postfix operation, and that will make your compiler the system to understand that we have that is an expression which could be repeated as many times as we wanted to have. So, if you want to repeat 0 times, you can have it. If you want to repeat 10 number of times, we can even have that. So, that operation is called the regular expression, which is going to be R star, where R is a valid regular expression, we put a star over that, which is an unary operation. So, by combining all these three, so it is possible to construct any regular expression which is very simple, or it can even be a complex one. So, that is about the regular expressions, and we have seen the construction of the lexical analyzer and regular expressions specifying token structures using regular expressions. So, when you are constructing regular expressions, the finite automata or transition diagram, we need to know what is a transition diagram and how the transitions are defined. You can even come up with the procedural representation which writes the program for the regular programs from the regular expression. And also the construction of regular expressions we have seen. In the later classes we shall see that is how we are writing regular expressions with the help of examples. And the questions component here, for any that is specified that is a language construct, that is your lexical construct, you may be asked to write the question, that your design of a lexical analyzer from your lexical construct specification. And another one is writing regular expressions from your that is your language description, maybe writing regular expression for identifier, writing regular expression for integer constant, writing regular expression for signed number, writing regular expression for the floating point numbers. So, these are the simple things which you have to focus, and I will give you more examples on coming regular expressions on the next episode. So, with this I conclude this episode. Thank you all.